Section 1. What it actually does, imagine a robot arm in a warehouse. Every day it tries to pick up a specific box from a shelf. Every day it bumps into the same corner, adjusts, and continues. Then tomorrow, same bump, same corner, same adjustment. The robot has no idea it has been here before. It treats every moment like the first time. RobotMem is a library that gives the robots persistent spatial memory. Not a bigger neural network, not a more expensive sensor array. Just memory. The ability to remember what happened where and use that information the next time the robot is in the same spot. Here is what it actually does in practice. The library maintains a spatial map. Think of it like a coordinate grid overlaid on the robot's working environment. When the robot takes an action and something goes wrong, a collision, a failed grasp, an unexpected obstacle, RobotMem logs that event with its spatial coordinates and a timestamp. That's the write operation. The read operation is where it gets interesting. Before the robot attempts any action, it queries its memory. Have I been near these coordinates before? Did something go wrong? If yes, it retrieves the context, what happened, how severe it was, how many times, and passes that to the decision layer. The robot can now adjust its approach before making the mistake, not after. In the demo on the GitHub repo, you can see a simulated robot navigating a room with several obstacles. Without RobotMem, after a reset, it relearns the hard way every single time. With RobotMem active, after the first run, subsequent runs show it slowing down near problematic zones, choosing alternate paths, or adjusting grip parameters in spots where grasps previously failed. The implementation is surprisingly lightweight. It's a Python library. The memory store can be as simple as a local SQLite database, or scaled to a remote store if you're running a fleet. The spatial indexing uses a KD tree structure, so lookups are fast even with thousands of stored events. You attach it to your existing robot control pipeline with a few lines of code. It's not trying to replace your planner or your perception system. It just sits alongside them, adding a layer of experience. What's counterintuitive here is the result. Developers working on robot reliability often assume the bottleneck is model quality, better perception, better planning algorithms. But RobotMem's creator found that a huge category of repetitive errors was not about the model being wrong in the moment. It was about the robot having no record that this moment had happened before. The fix was not intelligence, it was memory. Section 2. What it does not do. Let's be very direct about what this is not, because the name and the concept can lead to some inflated expectations. RobotMem does not make your robot smarter. It does not improve your model's reasoning. If your robot is making a wrong decision in a location it has never visited, RobotMem cannot help with that. It only helps with situations the robot has already encountered. No prior experience, no benefit. It does not handle dynamic environments well by default. If obstacles move, say a warehouse where pallets are constantly being rearranged, the spatial memory can actually become a liability. The robot might hesitate or reroute based on a memory of an obstacle that no longer exists. There are ways to implement memory decay and expiration, and the library supports timestamps for this reason, but it is on you as the developer to tune that. It does not do it automatically in a smart way. It is not a general-purpose robot learning system. It does not learn new skills from experience. It does not improve motor control. It is specifically and only about remembering negative spatial events and using them to modify behavior. It's a narrow tool solving a narrow problem. It also does not work out of the box with any specific robot platform. There's no ROS package, no integration with Isaac Sim, no plug-and-play connector. You are wiring this into your pipeline manually. For a research team or an experienced robotics engineer, that's fine. For someone who expected a drop-in solution, expect some work. And finally, it does not solve the problem of generalization across environments. The memory is tied to a specific spatial frame. Move the robot to a new room, a new facility, start from scratch. Unless you build some higher level abstraction on top, every deployment is a blank slate spatially. Section 3. What it could realistically do in the future. The foundation here is genuinely useful, and there are some straightforward extensions that would make this significantly more powerful without requiring science fiction. The most obvious next step is multi-robot shared memory. If you're running a fleet of robots in the same environment, they could all write to and read from the same spatial memory store. Robot A discovers a problematic floor tile. Robot B never has to learn that lesson independently. This is already architecturally possible with the current design. The memory store is external, but building reliable synchronization and conflict resolution for it would be meaningful engineering work. Another realistic direction is memory transfer between similar environments. Instead of starting from zero in every new facility, you could build tooling to map memory from one spatial layout to another when the environments are structurally similar. This would require some work on environment fingerprinting, but it's an achievable problem. Memory confidence scoring is another natural evolution. Right now, an event is stored. In the future, the system could weight memories by recency, frequency, and severity. A zone where the robot failed 6 months ago would carry less weight than a zone where it failed 3 times last week. This would make the system more adaptive without requiring any machine learning, just better bookkeeping. Longer term, this kind of persistent spatial experience layer could become a standard component of robot deployment pipelines, the same way logging and monitoring are standard in software deployments. If you're hosting your robot control infrastructure in the cloud, and increasingly people are, a shared memory service becomes a natural infrastructure component. Something like a managed deployment on DigitalOcean could make running a centralized RobotMem instance for a fleet straightforward, without needing to manage the infrastructure yourself. Section 4. Why it exists. The problem behind this project is something that anyone who has worked in operational robotics knows intimately. Robots are deployed in the real world, and the real world is not the same as the lab. In simulation and controlled testing, a robot's environment is perfectly repeatable or perfectly random. You can test for both. But in a real warehouse, a real hospital corridor, a real factory floor, the environment is neither. It has persistent quirks. A specific shelf that always vibrates when the HVAC kicks on. A floor tile that is slightly warped. A lighting condition near a window that consistently confuses a vision system at 3 p.m. None of these are things a model can predict. They are things that have to be discovered through experience. And the core insight behind RobotMem is that once discovered, there is no reason to forget them. Yet almost every deployed robot system does exactly that. Forgets. Because nobody built in a mechanism to remember. The creator's frustration was practical and specific. Watching a robot make the same avoidable mistake repeatedly, not because the model was bad, but because the model had no access to its own history. The fix was not to retrain the model. The fix was to give the robot a notepad. This is an honest engineering insight. It does not promise to solve general robot intelligence. It promises to solve one concrete, expensive, and very common problem in deployed systems: repetition of known failures. That is a problem worth solving, and solving it with a lightweight memory layer rather than a heavy model update is exactly the kind of pragmatic thinking that actually moves deployed AI forward.